Welcome to 2024. This is the first PHMass monthly meeting presentation of the year. As a reminder for folks new to us, we'll be doing these on the second Tuesday of every month for this year. I'm going to show a couple of our upcoming sessions here in a moment on what those topics are, but you can plan 6 p.m. on the second Tuesday of every month, put in your calendar, and hopefully we'll see you here for different presentations. So just starting off to set kind of the framework for the year, as I'm sure most of you know who have been attending our sessions, Passive House is now an approved pathway in the code. So as part of the stretch code is an optional pathway for all stretch code communities across the state, and it's a requirement in the specialized opt-in code for any large multifamily building over 12,000 square feet. You can see effective 1/1/24, so this January for buildings over 6 stories. So basically all multifamily buildings, 12,000 square feet or more in stretch code communities. So, or sorry, in option or specialized stretch code communities. So here's the current map of specialized stretch code communities. The ones in kind of a darker shade of blue with a yellow outline are the specialized code communities. And at the bottom of this, I know it's kind of small text, but at the bottom of this is showing you the effective dates. So this January 1st, just a few days ago, we had a whole section of towns that now went into effect. So you can read them here. It's the line starting with Acton and going through Wellfleet. Includes a whole bunch of different towns who is now the specialized opt-in code is code in those communities. That includes Boston, so the large one here. You can see there'll be a bunch more going into effect on July 1st, later this year. And then even one going into effect next year. But that's where we stand right now with the opt-in code. So this year, we're going to spend a lot of time talking about how we ensure success through this, make sure all these communities have successful projects going up. So join us for all that. This is some upcoming sessions. So February 13th, a month from now, we're going to have a high performance construction and trades training a session on sort of lessons learned from Ireland. So a special guest, Thomas O'Leary, will be speaking about a training center that they've set up there that's been really, really successful for high performance and passive house training. So we're going to hear a little bit about that and also hear about how hopefully we can get a center like that here locally. But there'll be more information going out through our newsletter about this session, but it should be a really, really good one about trades training, how we can be more effective at that. On March 12th, we're going to do an in-person session with our delayed speaker, our postponed topic. Kota Uno will join us in person at the BSA to give the presentation that we were going to have tonight originally before he had to delay it. So join us for that one. We're going to try to set this up one with a hybrid approach. So if you can't make it locally, you'll be able to attend just like this Zoom to hear the session. But if you can make it, you'll get to meet Koto in person and get to join the networking session that we're going to have before and after that at the BSA. Again, more details about that. And then the April 9th and May 14th ones are just there so you can mark your calendar. Check our newsletter for the topics going out soon on those ones. I got 2 more events to tell you about, 2 training sessions, and then I'll pass things off to James. The first is PHMass verifier training that's going to be held in person in Boston on January 25th and 26th, 2-day training. You can still register for this one on the PHMass website. But if any of you out there are looking to become a verifier, this is the time to do it. It's a highly in-demand role, and we have an in-person training right here in Boston. So sign up for this one. Pass this off to anybody you know who might be interested. Any HERS raters out there who want to become verifiers, this is a great next step, for example. And then the other one I want to bring up is the Passive House Trade Person Training. So this is just announced. Going to happen May 6th through 9th here in Boston. So this is going to be in-person trade person training. So you will spend, I believe they're organizing this to do 2 classroom days and then 2 days of sort of hands-on sort of mock-up construction building. So getting your hands dirty on trade person details. You'll also have the option to take the PHI Certified Trade Person exam and become a certified Passive House trade person through this program. We're currently working with EMU Systems out of Denver to host this. So they're bringing everything out here to do this program. And they're looking actually for a location. So we know we want to do it in the greater Boston area, We are looking for a host. There's some suggestions have been thrown around already, but if anybody out there knows of a good place, I know there's some suppliers that might have a large warehouse or something that we could use, but reach out, let me know, and I'll talk you through the details as we kind of look for a venue to host this. But those are the events that I had. Thank you for being here. I'm going to turn things over to James Peterson. Those of you who were at our PHMass Massachusetts Symposium this past December would have seen James speak, giving a really excellent presentation. There were some questions that came up from it. We did send around a version of this slide deck to attendees of the conference, so some of you may have kind of paged through it a little bit. But tonight, James is going to present this for us, walk us through it, and hopefully lead a pretty good discussion. Again, keep yourself on mute, but ask questions in the chat room. And at the end, you can use that whole raise hand feature, ask questions, and do that all the way. So I'm going to turn things over to James. James Peterson from Peterson Engineering, take the floor.
Thank you, Aaron. So if you're at the symposium, you'll have some context, and if you weren't, that's okay. This can be a standalone presentation. I have probably eight slides or so. I'm going to go through as quickly as I can, but take enough time to allow you to absorb some information, but really do want to leave some room for Q&A. Just a little bit more background on me. I am principal and founder of Peterson Engineering. We just celebrated our 32nd anniversary. And we're always been super interested in high quality building systems and energy efficient, sustainable, high performance buildings. So when Passive House came along, it was a great fit for us. And so we've been accumulating a bunch of Passive House, mostly multifamily projects. We have 10 complete, and then we have 17 or 18 in construction currently, and 17 or 18 in design. So they're adding up fast, and we're feel so fortunate to be in Massachusetts and benefiting from how progressive Massachusetts is. So that's enough for introductory words. If you could advance the slide, Aaron. Okay, so at the symposium, I shared at that time my idea of, I knew intuitively that if you extract heat from a space and use that extracted heat, let's say it's an apartment. In this case, maybe let's just stay with corridor. How about that? So if you extract heat from a corridor in order to make hot water, you have to replace that heat most of the time, particularly in the winter. And so, and if you're all electric, you're likely going to be replacing that heat with an air source heat pump. And intuitively, it makes sense that your net COP is going to be less than the sum of the COPs. But the goal here is to get at exactly what is that net COP and see if we can agree to that. So this is a diagram. The air source heat pumps on the left. It's moving heat from outdoors to a corridor. With the arrows, we're representing 1 unit of electricity in that's running a compressor. That's important part of the refrigerant cycle. That energy is added as heat to the refrigerant cycle, and that refrigerant cycle, through manipulating essentially the phase change temperature of a refrigerant, is able to extract heat from the outdoors and deliver that heat to the corridor at a different temperature, same amount of heat though. So we have three parts in, 1 electricity, 2 units of heat from the outdoors. And so on the right side of the air source heat pump, we see that we have 3 units of heat. So now we have a heat pump water heater on the right, and that moves heat from the corridor to the water. So we can deliver hot water to apartments. And that heat pump, for diagrammatic purposes, has a unit of electricity in, and it has what we're showing here is heat pumps that have a COP of 3. So for each unit of electricity in, they're producing three units of heat out. Or so another way of putting that, for each unit of energy in, we're getting 3 units out. So so here at with the heat pump water heater on the right, we're getting 3 units of heat out, and we're putting 3 in, 1 electricity and 2 heat from the corridor. So we have an extra, and this is going to feature prominently as we go on here, but we have an additional amount of heat that can go towards heating the corridor. So let's move forward. This is a little bit more about what I just explained. Let's see what else is in addition to what we were just looking at. Yeah, it's pretty much what we just went through. So I explained it on the previous slide. So go ahead, Aaron. Oh, could you go back? Because I want to make one key point here. So the third note, for a heat pump water heater with a COP of 3, 2/3 of the heat moved by the air source heat pump is utilized by the heat pump water heater. The unused unit of heat supplied to the air source heat pump stays in the corridor. So that's the key point here. So go ahead. So this is a formula. So you're going to see some other formulas. They're all essentially the same thing. But of the 3 formulas we're going to look at, they're the popular formulas for COP for 2 heat pumps in series. This is the one that I found to be most useful for me to understand what the net COP was. So each one of these pieces of the equation was helpful to me and represents something that is understandable. It might take some time staring at it. Took a little time for me, but it clicked. So in the numerator, we have COP2, which is the coefficient of performance of the water heater. And that represents the amount of energy that we're adding to the water. And then let's start with the denominator, which is a little bit more messy. So the one on the left represents the electricity used by the water heater. So if you recall, the COP of the water heater that we're using as an example is 3, and the 1 represents the unit of energy that we put in to get 3 out for the water heater. The next mass, COP2 minus 1 over COP1, represents the resulting energy that we're getting from the air source heat pump. The input energy of the air source heat pump that is benefiting us at the water heater. So the numerator in this COP2, which is COP2 minus 1, is the amount of heat that we're extracting from the corridor. So we're extracting, if you remember the diagram, we're extracting 2 units of heat from the corridor, and the other unit we're getting it from the energy we're using, the electricity in this case that we're using to make hot water. So that's the heat extracted from the corridor. The denominator, COP1, is the efficiency of the air source heat pump. And then this part of the denominator, the whole thing, COP minus 1 over COP1, and I'm going to move my people panel here so I can see my text here, is the fraction of the air source heat pump electricity energy that contributes to heating the water. So if we put numbers on this, we might do this in the following screen, but I don't think we do. So the COP, we decided arbitrarily of both these pieces of equipment is 3. So let's just see what we get here. So the COP2 is 3, minus 1 is 2, and that's over 3, 2/3. And I think we are going to describe this on a future slide, but let's stick with this one for a second. So 2/3. So that's the contribution or the fraction of the air source heat pump electricity energy that contributes to heating the water. It's also the fraction of the amount of heat that we're getting from the outdoors. We're basically getting 2 out of 3 parts that were input into the air source heat pump they're benefiting the water heater. Remember, we had that one unit that was an extra that was going into the corridor. So that's essentially what the minus 1 is. So I struggled with what the minus 1 was in this formula for a while. So maybe you will too. And this is courtesy of Mark Rosenbaum, the formula in this configuration. I'm appreciative of that because I was able to make sense of this one eventually. So go ahead, Aaron. So this was a popular version of how to calculate this COP of 2 heat pumps in series, and it struck me as a mess. This comes from a publication called, or an organization called Hydronics, Heat Pump Water Heater Fundamentals. And there's a link there that you can follow. And so this one I could not make sense out of like the last one. But it was something that popped up. It's the exact same formula as we were just looking at. It's just algebraically written in a different way. But the one thing you do see is that minus 1 popping up a lot. So let me go to the next slide. Matter of fact, I asked I haven't done any use of chat, but I did for this purpose download AI chatbot, and it was interesting how they responded. And my big takeaway was that they didn't get it right, and they apologized for not getting it right. They said sorry. AI says sorry too much, at least the version I have. Go ahead to the next screen. So just using algebra, young engineer in my office helped me with this. And I'm very grateful for that. So we're just using algebra to assure ourselves that these formulas are the same. So next slide. And so we're just doing another algebraic move. Next slide. And so now we end up with equation number 2. And it's Annalise Parsons from my office who not only helped me with the PowerPoint, but helped me with the math. So this is equation number 2. So when I initially asked my AI chatbot, what's the formula for 2 heat pumps in series, it almost had this equation, but it had COP1 times COP2 over COP1 plus COP2. It did not have the minus 1. I was like, to myself, I was like, this can't be right, because this is what I presented at the symposium. So if you imagine at the symposium, I assumed each one was a 2 in terms of COP. So if you ignore the -1 for a moment, COP1 times 2 is 2 times 2 is 4, and then COP1 plus COP2 is 2 plus 2 is 4, and 4 over 4 equals 1. And that's where I thought we were with heat pumps in series at the symposium. And so I knew that was wrong because I felt pretty confident that I wasn't quite there yet. So then, so this formula, and we get this from physics stack exchange, efficiency of parallel and sequential heat pumps, and then that has a link as well. And so I was still wrestling with what the -1. So when I told the AI that that was wrong, they came back with this one. And then I just innocently asked, what does the -1 represent? And then they came back and said, oh, and they removed the -1 and apologized. So I'm not can't trust AI yet. So next slide, please. Okay, go to the next slide. And then just using algebra, we divide top and bottom by COP1, and we end up getting the COP1 in the denominator on the bottom, and we get the COP2 by itself on the in the numerator. And this is the equation that we analyzed several slides back. So next slide, please. So this is a graphical representation. So what we all want to know is what happens when we're at various COPs. You might have a different COP for the air source heat pump than you do for the water heater. So this is how we're representing this. So if we go to the left set of dots, there we're assuming each piece of equipment has a COP of 2. And then you can see the blue line on the bottom is the net COP. So when you have 2 and 2, the net COP is 1.33. So it's not 1, it's 1.33. So the next example is we assume both have a COP of 2.5. And when those are in series, we're 1.6 or somewhere thereabouts. And then I was interested to know is if we had heat pumps in series, but one was better than the other and vice versa, what happens? And what we showed with this is that we got the exact same results, 1 2/3, something like that. So that's when we have one piece of equipment at 3. You can plug in these numbers. So this is the case, it's 3 and 2.5. So you can plug them into that formula on the previous page, and you can get the precise number. But when we reverse those, we get the same number. And then if we assume we have COP of 3 for both pieces of equipment, we have a resulting COP of 1.8. So this is, I think, effective representation. And you can plug in higher numbers, lower numbers to get the net COP. So next slide. All right, so I do want to just touch on this because this was something that was also covered, and it's been a concern of ours at Peterson Engineering, and we have not been recommending hybrid heat pumps in apartments, and the reason is because they create an uncontrolled cold draft, and it's not insignificant. So we're going to show the math to demonstrate the significance. So next slide. So if we just hypothetically say that, we're going to use 20 gallons and of hot water, and the inlet temperature is 45 degrees, and we're going to heat that to 110 degrees. How much energy is required to do that? So the formula is as follows. We take the gallons, we take the temperature difference, the temperature we're rising it from and to. 45 degrees is a common winter temperature. It's probably what you're getting out of your cold water faucet today. And then specific heat is the is the heat capacity of the substance. In this case, it's water. And water is a wonderful thing, but unfortunately, in this case, it has a very high capacity for heat, which means it takes a lot of energy compared to all other common substances, including rock. It requires a lot of energy to raise it one degree. And then we have a conversion, pounds per gallon, in order to get the units we want. So, and then there's the actual numbers, and we're ending up with almost 11,000 BTUs to raise 20 gallons, that amount. So let's go to the next slide. So now on this slide, what we want to do is we want to demonstrate how much cold air that results in. So in order to heat that hot water, we're extracting that heat from the space. And I'm just going to skip down to the specific heat. So in the case of air, the specific heat is 1/4 that of water, meaning that we only need 1/4 the amount of energy to raise a pound of air 1 degree Fahrenheit. So it has 1/4 the capacity. In this case, that hurts us because we're going to create, a pound of air is roughly 7.5 cubic feet. And we're going to pay for that in cold air. The fact that air has a dramatically lower specific heat than water. So let's go back to assumptions. So a pretty comfortable assumption is that the temperature of the apartment is 70 degrees. And that represents our entering air temperature, EAT. That's the air temperature that's entering the water heater. And then 55 degrees, in talking with one manufacturer, is a pretty typical leaving air temp. And that makes sense to me. That's a very common leaving air temp for HVAC equipment. And at coil temperatures less than 55, you can get latent heat removal when there's moisture in the air. And so that's another reason why a 55-degree discharge makes sense to me. So that's our leaving air temperature. So we're reducing our air volume, which is, if you go down to 4, this is also from one of the manufacturers, it's about 200 CFM. So we're reducing 200 CFM by 15 degrees. And so what I was curious to know was how long can we expect a water heater to reduce 200 CFM by 15 degrees? That's the cold draft. And how long is that going to last? So we plug all this information into the formula, which is, and what we want to do is get how long. So we're formulating the formula in order to get time. And when you plug all that in, it's 200 minutes or 3.3 hours. So there's a significant amount of cold air. And what's important and what's discouraging about that, it basically represents uncontrolled source of cold air. So one point that I made at the symposium is that, we're aiming to make buildings better. And so this is a step backwards in that we have an uncontrolled source of cold air. I mentioned that we're working on projects where we have an uncontrolled source of hot air in 2-pipe systems that don't have individual shut-off valves in fan coil units. So you essentially get heat in apartments when you don't need it. So we're replacing those systems with systems that can, eliminate the uncontrolled heating. So we're heading in the wrong direction if we have an uncontrolled source of cold air in an apartment. And we think that not only, we think because we don't have a lot of examples, but we think this is going to result in cold drafts or uncomfortable to most humans most of the year, certainly 3 seasons out of the year, and also parts of the summer. So let's see, that might be my final slide. Can we check, Aaron? Looks like it's our final slide.
That's the last one.
Okay, so let's keep the slides handy in case we want to reference them, Aaron, but I think we can answer questions. And how are we doing on time, Aaron? How much time do we have left?
We have plenty of time left.
Awesome.
So
That's
folks, do
great.
not hold back. Let's hear some questions.
Aaron, you can take the slides down, maybe see more faces. Thank you. Well, let me prompt somebody. Are people surprised that our COP, if we go back to net COP, are people surprised or disappointed, or do you think the number can't be right, or do you have you think our math is wrong? Because I haven't seen this well represented in the work that we're doing to electrify buildings. Basically, this phenomena that I decided to focus on. Also, so far, this is a robust Q&A session.
Yeah, no one's jumping in with that question. There is one in the chat room though, which is kind of, you know, helping to maybe approach a solution here, a question about it. Does this favor a more centralized system than instead?
Boy, that's a question we've been asking ourselves, because the electrification of domestic hot water is a relatively new thing. Let's say 2 years, maybe 2.5. And this is a disappointment to us, because in an ideal world, we would have a good local solution for electric heating of hot water. And we do not have a good, in my opinion, we do not have a good local solution for heating of domestic hot water. We do have an okay central solution. And the reason it's okay is because it doesn't have it hasn't been around a long time. So we don't have the level of confidence that we'd like to have. But there's more than one manufacturer that makes basically commercial scale air source heat pumps that heat water. The one we have we like the most uses CO2 as a refrigerant, and the unique thing about that is with the typical refrigerants, air source heat pumps cannot make hot water. They can make 120-degree water, and when you ask them to make more than that, they're really struggling to do that. The CO2 as a refrigerant, we have no trouble making hot water, and in fact, those equipment that's using CO2 is not allowed to make hot water hotter than 160. So they could if they were allowed to. So that's a nice improvement in technology, is that we're able to get hotter water from a heat pump. And so we have those designs on many of our projects, but again, they're a little out there because they don't have much of a track record. So from my perspective, things aren't looking good from an equipment standpoint for electrification of domestic hot water. So what are we doing? We're looking at other opportunities. The Mass Plumbing Code, which is my newest and favorite one. The Mass Plumbing Code recently was updated, and in that, it allows engineers to engineer domestic hot water distribution systems. And that means we can take a tremendous amount of piping out of buildings. So it helps us with our reduce embodied carbon. It helps reduce costs. These central heat pump water heating systems are expensive, both the equipment and the space they take up, and the weight that the weight of them that requires a more robust structure. So the plumbing code for decades has not been adapted to the reduced water use of fixtures. And now now as engineers, we're able to engineer domestic distribution systems, and they're going to be dramatically smaller. So that's one example of where we can make things better.
That's great. And we're now starting to get a lot more questions coming in here. I got a few in the chat room. We also have someone with their hand raised. So I'm going to try to get through these here. So first, James, is it practical to just exhaust this air outside in these apartment buildings?
No. And the reason is something called conservation of mass. So when we exhaust air out of building, we're exhausting something. Air is something. So we have to replace that air. So if we exhaust it, we have to introduce it. So that's not an option. Some other options we've heard is, discharge the cold air into the return side of the fan coil. But the 200 CFM for 3 1/3 hours, that still represents an uncontrolled source of cold air, because we're either going to be discharging that out of the return air grill because the fan's not on, but if the fan coil fan is on, we're supplying cold air to spaces that aren't asking for cold air. We've also heard the notion of dumping it behind the refrigerator, but your refrigerator is like a really good Yeti. It really doesn't use much energy, and there's therefore not a whole lot of heat behind the refrigerator. Nowhere near, I don't know what the factor is, probably 50. Nowhere near the amount of heat we would need to offset the cold air that we're producing.
Actually, is a suggestion here as well, thinking could a refrigerator company here work together and try to solve this? Maybe
only if you left in the fridge. Only if you left your refrigerator door open.
Yeah.
But you don't want to do that.
Let's see. Actually, I'm going to go now to Chris. You have your hand raised. If you just want to ask your question directly, you can.
Hello, can you hear me?
Yes.
Yeah.
Great. I'm wondering if you've looked at SunAmp or other phase change material hot water heaters.
Can you say that name again?
SunAmp.
I am not familiar with that. Tell us about SunAmp.
My understanding is that they have over 20 years of history in Scotland, but basically it's a phase change material to store the heat, and could be powered either by hot water or electricity.
Yeah,
So it'd be using an electric resistance, so you're not having the high, COPs.
Yeah, we'll check that out. At their core, refrigerant cycles are manipulating the phase change of a material. That's fundamentally what the refrigerant cycle is. But we'll check out that manufacturer. Thank you for the suggestion.
Yeah, so it would just be the phase change material. It would not have a refrigerant. So I think the main savings is space, maybe 1/4, 1/3 the traditional size of an electric resistance hot water heater.
Yeah, I'll check it out. But just to be clear, refrigerant is a generic word for a material that has attractive qualities for manipulating its phase change to benefit what you're trying to do. But we'll look into that. Thank you.
Question here in the chat. So this is about experience where regulators are asking for systems like this, hybrid heat pump systems. In your experience, what is their awareness of this issue? regulators, code officials, others, are they aware of this, or is this just not something that's well known?
Apparently not well known. And that's what we're trying to get the word out. We're not trying to get the word out that this is no good. What we're trying to do is get the word out, basically what the physics are, what the math is, and let people make decisions on what's an appropriate application. And we all want electrification to be successful. We want buildings to get better. You know, there's pros and cons, and I guess what we're talking about tonight is a con, and it's just something we need to be aware of. To specifically answer the question, here's a couple anecdotes that we've run into. We've heard that the city of Boston, and I was on something like this where the city of Boston was accepting hybrid heat pumps in apartments, and so that's influential. So they've been influenced to accept these, where we have not been influenced to accept this. We're the opposite. We're motivated to get the word out that this is not a good thing. Another anecdote that occurred recently was a client of ours, and his point was, James, you're recommending that we don't do this, but our other engineer says it's fine. So that's a problem. So our peers, we have to get on the same page with our peers. And we actually met with that engineering firm and shared notes. But that has caused confusion for users and for architects, that they're getting different stories. So that's one of my goals, is that we can look at the facts, we can agree on the facts, and what I don't want to see is I don't want to see too many mistakes. You know, I don't want to learn late. We'd rather wave the flag early than just say, well, people will figure it out. So we're trying to help here.
Gonna go to Hank. You can ask a question.
Can you hear me now? Yeah. So, James, to push the point, what happens if you've got 10 or 12 units on a corridor and you set up these heat pump hot water heaters so they're all exhausting into the corridor? Is the corridor now just a complete refrigerator, or is it something where it would be tolerable?
Yeah, so Hank, we've actually done this design. One of our early passive house designs used this technique. And the reason why we liked it at that time was the corridor is a transient space. People aren't sitting on a couch relaxing and requiring comfort like they do in the corridor. So we felt that the corridor is a transient space. We don't have the same requirement for comfort in the corridor. We could let the corridor temperature depress lower than 70 and we'd be okay. So comfort, it doesn't present the same challenge. But in order for the COP not to dip, we can't be, we don't want to be using, say, 60-degree air or 55-degree air. Our COP is going to dive in terms of the COP of the water heater. And so we still have to add heat into the corridor with an air source heat pump, presumably. So we still have the basic problem with 2 heat pumps in series.
Right.
And that's what we did on a couple early small 30-unit passive house projects, is we added extra heat in the corridor. The corridor doesn't generate a lot of heat. Usually they're double loaded. Usually they're not given the benefit of a outside wall, because why would you do that? So lighting is really the heat contribution to the corridor. So there's not much heat source in the corridor.
And what about the dropping back to, there's a lot, what we understand is that specifically in market rate units, developers are very committed to the idea of putting all the utilities onto the resident.
Yeah.
And so what happens to the overall COP of a situation on somebody's meter in the unit if they just have an electric resistance hot water heater in addition to their heat source for their hot water heat source? I mean, their hot air heat source.
Well, then you have an air source heat pump that's going to have its COP, which is going to vary based on season. And the COP of the water heater, if it's electric resistance, will be 1, essentially.
One.
Yeah.
So you might have a situation there where it almost sounds as if that might end up with a combined COP that is better than some of the ones you showed on that graph.
It might be in the same ballpark, and depending on the outdoor ambient conditions, it might be better or worse.
So that's actually, it may not be too much worse than what you're showing. And if a market rate developer does it that way, they at least avoid the uncomfortable cold air.
Yes. The other thing that's the reason why they're called hybrid heat pumps is because they can run in heat pump mode and they can also run in electric resistance mode. So what can happen, there's a solution there. If there's a comfort problem, the landlord can switch these pieces of equipment to electric resistance, but you're not benefiting from part of what you bought.
Can that be done on a timer so that you only produce the draft in the middle of the night?
Yeah, I think we can do that thought exercise. So, that might work out for some occupants. People, most of the water is used around dinner time and early evening. That's the most common use of hot water, kitchen activity and showering. So in that case, you're going to replace that hot water overnight. And then the other time is first thing in the morning. That's when you have people getting up and going to work. So apartments might be empty during the day, and but now post-COVID, there's probably a lot more people in their spaces than there previously was, and that's probably going to continue. But you could do some thought exercises and see if you can allay some of your concerns based on occupancy. One thing that Hank, we're advocates of is we're generally skeptical of controls or complex solutions because in our experience, the more complex a system is, the less chance it has of a good outcome. So we have to keep that in mind too.
Yeah.
We're going to go to Mike. You can ask your question.
Thank you. Can you hear me?
Yeah.
Right. James, thanks very much for walking us slowly through those equations. Actually put the equation of interest into a spreadsheet. And yes, indeed, it produces the outputs you said. So thank you for that. And a couple of other things. One is 10,000 BTUs of heat taken from the apartment might not mean something to people. But if you frame it as in the example you showed, needing to take 10,000 BTUs of heat from the apartment, let's say you have a window air conditioner of 5,000 BTUs an hour capacity. It's running that for 2 hours. So how would you like to have that going in your apartment in the middle of winter?
Yeah,
So,
that's a great point. I wanted to add this, but you got to draw the line somewhere. But we could probably take a cooling load calculation and discover that most of the time in the summer, the cooling load could have a chance of being less than the air conditioning provided by the uncontrolled source of cold air. The problem with the problem is that we don't necessarily have a coincidence of need between when the cold air is coming from the water heater and when the human occupant would benefit from dehumidification and a lower temperature. But you're right. Thanks for that context. 10,000 BTU and 20 gallons is 20 gallons. You can plug in your own numbers. You're all welcome to these formulas. I don't own them. They're basically laws of nature. Put your own numbers in and you know, play with them.
I'd also like to point out to everyone here, I don't know who else is here, you're addressing the situation of multifamily, which is much different from a single family home with a basement into which you would put this hot water heater, because it has beneficial effects down there in the summertime when it's dehumidifying and cooling off the basement and keeping things nice and dry. And in the winter, it really doesn't depress the temperature that much. You know, I've got data from this, and it's not a bad thing at all. But in your living space, it's something else entirely.
Yeah, thanks for adding that.
There's a comment here in the chat, just wondering about possibility of preheating some of the water before it even gets to the tank, say through a solar thermal, you know, collector. Would that change the outcome here? Absolutely.
So if we think about, I don't know if you can do this, Aaron, but if we go to that, I think the last slide. Yeah, this one. So no, go to the previous one. Thank you. Okay. So we're talking about taking water from 45 degrees to 110. If we can do something that raises that 45 degrees to like halfway, we're basically reducing that 10,009 by half. So wouldn't that be a wonderful thing? So one of the things that I wish had more traction, and I'd like to see more support for in terms of incentives and more engineering work, is on drain water recovery. So drain water recovery is basically wrapping your water line around your sewer pipe. I know it sounds like, boy, that's too close for comfort, but it's pretty effective. And it also meets my criteria for being relatively simple. It's surprisingly expensive because you're using a lot of material. There's also some different configurations, but that's an idea for raising that water temperature. You know, in the summer, just to give you more information, in the summer, the Boston water temperature or Eastern Mass, it's coming from a reservoir. It probably gets into the high 70s. So that range of entering water temperature varies seasonally. If you have an iced over reservoir, and that's the only source of your water, it's going to be around 40 degrees as long as the reservoir is iced over. So the point I want to make about solar pre-tempering is you can do solar pre-tempering, but the times it's going to benefit you most are not the times when you need it most. So we've all survived November and now December. Part of what makes them terrible is the shortage of daylight, but also the sun is so low in the sky. So they're terrible months for pre-tempering when we need it the most, when our temperature is the lowest. And January's nothing to write home about, and things get a little better in February and March. So there's some drawbacks to solar and when it's most available, and it's at the least, it's when we need it least. But it would be a benefit.
And a few questions just relating to, I guess, new technology and costs coming down in the marketplace. You alluded to, I mean, centralized systems still being a little out of reach for some of these types of units, and also the CO2 coolant method, which is also kind of a little hard to come by. Do you have any insight into when some of these things may be more affordable, or when the technology may get to the point where we can do this centralized?
Yeah,
How
so
far down the road are we looking here?
let's see. The manufacturers are hustling. I can tell you that, because the electrification thing is moving very quickly in Europe and also now in the US. So they're working really hard. The other point I want to make, which is back to my point about the mass plumbing code changing, then that will allow us to bring down the cost of distribution. What we can do also now is we can use better information to make sure we're not oversizing domestic hot water systems, and that brings down the cost. So the data available to us is getting better. What I've always liked to do with domestic hot water is allow yourself some flexibility to add an extra tank if you need to. But the requirement for domestic hot water varies widely between buildings, and it's hard to nail down. Engineers like to oversize things, so we can do a better job in making sure that the domestic hot water plant isn't bigger than it needs to be. The reason why oversizing with gas doesn't burn you, no pun intended, is that gas-fired equipment has gotten smaller and smaller over the last 30 years. And it's amazing how much heat you can generate from a relatively small appliance. So gas equipment was headed in a attractive direction, in that we could make darn sure we had enough hot water without it costing us a lot and without requiring a lot of storage. Storage is surprisingly expensive. So hot water systems tend to be high on recovery, which is the ability to heat, and low on storage. And because air source heat pumps, even the CO2, don't recover quickly, we need to store a lot of water. And storing water, like I said, is expensive. So we have slow recovery times that require larger storage. But one thing that we're hoping for with manufacturers is that we have more equipment available to us. Do I know when it's going to come? I can look to air source heat pumps and maybe use that as a maybe as a predictor. Mitsubishi came into the marketplace very early, and they invested a lot of money in Massachusetts, probably 20 to 25 years ago now. And we've seen a lot of additional manufacturers come into the marketplace with varying levels of support. So what we need is, we not only need quality equipment, we need the service. We need trained service people, we need parts, and we need to be confident that there's a reasonable chance this service and parts is going to be available for the life of the system. And so that's likely the way it's going to trend, is that it's going to trend. We'll have a few serious players that really provide the support, and we have more choices than one or two. But currently, we feel that we still only have two choices with air source heat pumps and multifamily, where we have the two things we require, which is a high quality system and the support required to service the system over the life cycle of the system, which is 20 years. That's a long time.
I'm curious, have you compared any of this to more of like a tankless electric system, an on-demand system? Does that change any of the calculations?
Unfortunately, no. So tankless is pretty much electric resistance. So you get a little less standby losses theoretically. but with a really well insulated electric resistance tank, the standby losses are pretty nominal. So, and you also, if the number of units is not enormous, like 250 or something like that, you're going to negatively impact the service, the electrical service size to the building.
There's a comment here then about the cost of electricity, which comes up a lot when we talk about electrification. We're putting a lot more on the grid and away from gas, and electricity is more expensive. And as more people switch to putting gas fuel things onto electricity, they're worried that it may go up. So there's a question about that, but I'm curious to frame it in the sense that you've been talking about COP of these units, and you've been throwing out numbers 1, 2, 3. And I wonder if you could just briefly explain what that means in comparison to, say, a gas boiler of COP1. I mean, we're talking about something that's more efficient. So ideally, the cost might be a little less because you're using less power. Is that right?
Yes. So the higher the COP, the less energy, less electricity in that you need to move the heat from one place to another. There is a physical limit to how high your COP can be. So you would think intuitively that if your air source heat pump was being used to make heat in the summer and it's hot outside, it would have this like crazy high COP. And that's just not how it works, and for reasons I don't understand. But the theoretical or the physical limitation to COP is like something north of 4. So it's pretty disappointing. So one rule of thumb I'd like to give people is that and people have been thinking about COP in this way for a long time, especially when they're thinking about cost of fuels. If you have a COP of 3 for a heat pump, and the cost of gas is 3 times less than electricity, and gas appliances, if you assume they're in very round numbers 100% efficient, then the cost of electricity and the cost of gas is the same. So your COP of 3, or they're in the ballpark. So historically, that's oftentimes been the case, that gas is about, or electricity is about 3 times more costly than gas. But that's changed. I don't know what it is today, but in recent years, it's been more like a factor of 5. So I'm not presenting on that tonight, but another thing that we need to be cautious of is the cost to consumers of electrification. And we had an RFP come into our office, and we're scratching our heads about it. It's being referred to as a deep energy retrofit, but it's in a commercial building. The scope only includes the replacement of a steam boiler with a ground source heat pump. And we're wondering how to approach that, because that doesn't meet our definition of a deep energy retrofit. So what we have seen with air source heat pumps is a misunderstanding by the general public and also people within our industry that you can just add air source heat pumps and you're going to save money, and that's not the case. So it has to be a whole holistic approach. I think most of this audience understands that because of the cost of electricity compared to gas. There was one more comment I was going to make about that. I've lost track, so maybe there's
all right. As you think about it here, I'll just note, thanks Laura in the chat room for bringing this up. In addition to anything around cost or performance issues switching from gas to electricity, there are without a doubt health impacts. We've talked a lot about the health impacts of gas around, say, gas stove tops and gas ovens for cooking, but it's same thing applies for your gas boiler for either heating or hot water. Switching to electricity is certainly going to be better health-wise for indoor air quality.
Oh, totally. So I have 2 daughters. They're older now, but when they were younger, we had a gas stove and a galley kitchen. So the way to get from one part of the house to the other was was running by the gas stove. And I was always paranoid that they'd either turn the gas on or turn the burner on. And we also had a gas dryer. So, and now we have a wonderful induction stovetop. And so I totally agree with all of that. So very early in my career, someone put it well when they said, everything about using electricity is great, except the cost. So it's amazing what there's so much flexibility in how electricity can be used to heat a space, how it can be used to cool a space. No other fuel source has the same flexibility as electricity does.
So I'm going through the chat, and I think I got most of the questions here. My apologies if I didn't get any of yours. If you might maybe just re-put it in there so I see it again. But I'll give one final call here. If anybody does have additional questions, put them in or use the raise hand feature. You can get them out. Gonna give it one moment. I'm not seeing any come in here. This has been a good discussion. I know after there were some comments, and questions to you at the symposium, and afterwards you put together this deck and got it out to us. So that was very, very great. And I'm appreciative that we actually did have the time here tonight to have you walk through it. Because I think that was a deck that really needed to be walked through rather than just so that was good. I don't have anything to add. Thank you everyone for being here. James, any final comments you'd like to put in?
Yeah, just thank you everybody for paying attention. This is it's kind of heavy on the math and physics, and it took me some time and some heckling to really get to the bottom line. But I'd love to entertain people's feedback, and would love to get more feedback. So if people have been too shy to ask a question or want to spend more time with it, I've got a pretty basic email address. It's james@petersonengineering.com. The only thing you have to remember is my last name is spelled S-E-N. So I'd love to receive an email with any follow-up.
Well, thanks so much. There was a final comment here saying, thanks, James, we like math and physics. So I think you're in the right group for tonight's presentation. Thank you. Everyone take care. We'll see you again for a virtual presentation in a month, and then for a live in-person presentation in March. Take care.
Good night.